In this video, we'll be going through the 2019 Wave Systems paper. Sarah builds a simple guitar using a hollow wooden box as a resonator and 3 strings on a wooden fretboard. She fixes the strings between 2 bridges that are separated by 0.736 meters. And as usual, we're not privy to the actual image, which is for some reason from eBay, but I can imagine that we'd be looking at some sort of guitar where the length of the 3 strings is our 0.736. There you go, I think that's a worthy replacement. In the space below, sketch the 4th harmonic that is formed when a string is plucked. And so the 4th harmonic features 4 antinodal spots and looks a little something like this. The speed of the wave through the string is 289 meters per second, and we're asked to calculate the wavelength and the frequency of this harmonic. And so, knowing that our total length is 0.736, a full wavelength here is going to be half of that, which gives me 0.368 meters. Now to find our frequency, we need to use the equation that the velocity is equal to the wavelength times frequency, where the frequency is the velocity divided by the wavelength. Putting in our numbers gives me 785.32, rounding that to 3 significant figures because that's what we're given in the question, gives us 785, and the units are, of course, hertz. The 3 strings of the box guitar produce different fundamental frequencies when played, even though the strings are the same length and are made of the same material. Use the equation below to explain how this is possible. So this equation is quite nice. It gives us our velocity there, our tension, and mass per unit length. Because the mass per unit length is a reflection of the material, and the material is the same apparently, we can assume that the mass per unit length is a constant, but that it is the tension that is variable here. The tension is changed to produce a changing velocity, and a changing velocity, given that velocity is equal to frequency times wavelength, the wavelength doesn't change because the length of the strings are the same, so that means our frequency must change. So a changing tension, in other words, produces a changing velocity, and within that a changing frequency, given that the mass per unit length is the same because it's the same material, and the wavelength is the same because the length of the string is the same. Let me put that into a nicer sentence. Since mass per unit length is the same material, and wavelength is the same string length, increasing the tension will result in an increase in frequency. Sarah wants to tune the D string to the frequency 147 Hz. She plays a 147 Hz tuning fork, then plucks the D string on the guitar. She notices a pulsating loudness twice every second. When she gradually increases the tension of the string, the pulsating loudness becomes less frequent and then disappears. Explain the phenomenon, which is beating, that causes the pulsating loudness, and why the increasing tension of the string makes it disappear. A calculation of the original frequency of the untuned D string should be included in your answer. So of course the phenomenon here is beating, and beating describes the fact that when you have 2 frequencies existing in the same space, if you're standing in a single spot, then the waves will alternate between constructive interference and destructive interference as a function of time, and you'll notice a pulsating loudness as it describes in this question. The beat frequency itself is very simple to calculate. It is just the difference in the two frequencies. And given that she increases the tension of the string, and the pulsating loudness becomes less frequent and disappears, means that she's increased the tension of the string and increased the frequency until it's matched 147, which means the untuned D string must have been lower than 147. Given that the pulsating loudness is twice every second, that means it must have been 145. But let's express that mathematically. When two different frequencies are present, an observer will experience alternating moments of constructive, loud, and destructive, quiet interference. This is called beating. The beat frequency is the difference between the frequencies. As Sarah increases the string tension, its frequency increases to match the tuning fork. As the difference is now 0, the beats stop. Question 2. The speed of sound in air is 338 meters per second. Sam and Miracle are experimenting with a 0.446 meter length of plastic pipe that is open at both ends. That is an important bit of information. When the wind blows across the top of the pipe, Sam and Miracle hear a sound. They assume the sound is made by air inside the pipe resonating at the fundamental frequency. Show that the frequency of the sound is 379 Hz. So let's first draw what the fundamental frequency looks like in an open-end pipe. And so as we can see, we have an antinode at both of these ends and a node right in the middle. And what we are looking at in terms of the actual wave is we have a trough here going to a peak here, which tells us that the length of the pipe encompasses half a wavelength, given that a trough to a peak is exactly half of a wave. And so to find our wavelength, we just need to solve this for L, which isn't terribly taxing. Putting our number in gives me 0.892 meters. To find our frequency, we need to use the relationship that the wave speed is equal to wavelength times frequency. Solving that for frequency gives us velocity divided by wavelength. Given that we know the velocity from up here, we can just put in our numbers, which gives me 378.923. Rounding that to 3 significant figures, which is what we're given in the question, gives us 379, and that's Hertz. Sam places his hand over the end of the pipe, and the frequency of the sound coming out of the pipe changes. Describe and explain the changes in the frequency of the pipe, and draw diagrams to support your answer. Well, let's start off by drawing the fundamental frequency for both an open pipe and a closed pipe. Now, as discussed in the question above, the length of the pipe contains exactly half a wavelength for our open pipe, such that our wavelength is twice the length of the pipe. For our closed pipe, however, this section here is only a quarter of a wavelength, which means that a wavelength needs to be 4 of these lengths to make up a full wavelength. This shows us that a closed pipe will have a higher wavelength than our open pipe. A higher wavelength, therefore, means a lower frequency. Let's try putting that into words. The closed pipe has twice the wavelength, and via V equals lambda F, it has half the frequency, assuming constant velocity. Sam removes his hand so the pipe is open at both ends again. A strong gust of wind blows across the top of the pipe and causes a much higher pitched sound to be produced. Miracle uses an app on her phone to determine that the frequency of the sound is 1138 Hz. Draw the new standing wave formed in the pipe on the diagram below, and also identify the harmonic that is resonating in the air column. Well, to do this, we first need to identify the harmonic, which involves finding what multiple of the fundamental frequency 1138 Hz is. And so our N, which is our number of our harmonic, is going to be the frequency that we have heard, divided by our fundamental frequency, which we determined in part A to be 379. Putting our numbers in gives us almost exactly 3. In fact, to 3 significant figures, that's 3.00. So make a note, we are looking at the third harmonic. Now, for an open pipe, the third harmonic is going to have 3 nodes. So let's try and draw this. Sam has the idea that if he holds the pipe while riding his bike really fast, he can recreate the same frequency in the pipe that the gust of wind had produced. Holding the pipe, Sam rides away from Miracle at a speed of 12.2 meters per second. Sam hears the pipe resonate at a frequency of 1138 Hz, which is what we were experiencing in the previous question. But Miracle measures a different frequency. Calculate the frequency that Miracle would measure and explain why the two frequencies are not the same. And so if you haven't already cottoned on, this is a Doppler effect question. And so kind of like the previous question, I'm going to flip this around and I'm first going to explain and then I'm going to calculate, just so I don't forget this part really. As Sam rides away, the waves ahead of him become closer together, and behind him, where Miracle is, they become further apart. Miracle thus experiences a higher wavelength and lower frequency. This is called the Doppler effect. Having got that out of the way, let's now calculate the exact frequency. So let's write what we are given. The velocity of the source is 12.2 meters per second. The original frequency, which I'll call F as is convention, is 1138 Hz. All the way above, we were given the speed of sound, which I've already forgotten, and that is 338 meters per second. Velocity of the wave is 338. And that's all we need. The equation on your formula sheet that we're going to use looks like this. Now, the tricky bit with this equation is often remembering whether or not this plus or minus should indeed be a plus or a minus. One way to think of this, one way to remember this, is to visualize Mr. Wibbly with an axe. If Mr. Wibbly with an axe is coming towards you, that is a pretty big minus for you. If Mr. Wibbly is going away from you with his axe, then I'd consider that a pretty big positive. So because Sam is cycling away from Miracle, this is indeed a plus. Putting our numbers in gives us 1098.355. Rounding that to 3 significant figures, because that's the lowest amount of significant figures that we're given in the question, gives us 1100 Hertz. Question 3. Lasers are used in scientific research, and we've got a bunch of waffle about that. And we're given a diagram of a laser and a diffraction grating, which is all pretty standard. The picture above shows 3 different colors from top to bottom. We have violet, green, and red. And so we have increasing frequency in that direction. And that light is shone through the same diffraction grating. And just before I even know what they're asking, we can see, of course, that the lower frequency red has diffracted a lot more than the higher frequency green, which is diffracted more than the higher frequency violet. So of course we have this relationship between diffraction amount and frequency. Describe using physics principles why the violet maxima, the bright spots, are closer together than the red maxima. Well, that's essentially what I was just talking about. Though in addition to just stating that as a fact, we can also look at the mathematics of that with the equation n lambda equals d sine theta, where for the same order number, if we have a decrease in wavelength and the same diffraction grating, so the same slit separation, we would also have a decreasing angle, which, as a mathematical side note, only really works because we're talking about angles between 0 and 90. Of course, sine is a little bit more complex than that, but this simplification at least works for this purpose. So let's put that into words. As the above equation shows, a reduction in wavelength results in less diffraction and a smaller angle. Violet has a shorter wavelength, so its antinodal lines, bright spots, have a smaller angle between them. The diffraction grating has 400 slits per millimeter, and the angle between the center and second order maxima is 20.7 degrees for the violet laser. Show that the slit separation of the diffraction grating is 2.5 times 10 to the minus 6. So this 400 slits per millimeter is really just our N. And to find our D, our slit separation, our D is simply going to be 1 over N. But of course we want to have this in meters, which we can approach in a couple of different ways. I personally like to think of it this way. We have 400 divided by a millimeter, and we know that a millimeter is 0.001 meters, which would give us 400,000 per meter. Now, flipping this over, we'd have 1 over 400,000 per meter, which gives me 2.5 times 10 to the minus 6 meters, and is exactly what we're trying to find here. Next up, calculate the wavelength of the laser light. So let's write what we have. And the equation we're going to use is the one we referenced in the question above in A. Solving that for lambda just involves dividing both sides by n, and now we just need to put in our numbers. Which gives me 4.4184, rounding that to 3 significant figures, gives me 4.42 times 10 to the minus 7 meters. Explain the role of diffraction and interference in producing interference patterns seen when light passes through a diffraction grating. And so you'll find one of these questions in every one of these exams, where it's basically wanting you to give the textbook definitions of interference and diffraction and how that links to nodal and antinodal, constructive, destructive, peaks meet peaks, trough meets troughs, and so on. So let's just launch into an answer. As light hits the diffraction grating, it passes through its numerous slits. The light from each slit diffracts in a curved pattern and interferes with the light from the other slits. Where the path difference is a whole number, constructive interference occurs, and an antinodal line is formed. Where the path difference is some number 0.5, destructive interference occurs and a nodal line is formed. The wavelength of the light from the green laser is 5.32 times 10 to the minus 7 meters. Describe and explain what would be seen at a point 28.6 degrees from the center of the green interference pattern. A calculation should accompany your discussion. Okay, so let's of course write down what we know, recycling some of our values from above. I'll put them here so I don't have to keep scrolling up. Okay, so what we want to do is we want to find out what our n is given this diffraction grating and this angle and also this wavelength of light. The value of the n will then tell us whether or not this is a antinodal point, a nodal point, or something in between. So let's calculate that using our now familiar equation. Solving for n by dividing by wavelength, and now putting our numbers in, which gives me 2.249, which is basically 2.25. So what that means, say if we have our pattern going like this, where we have our n equals 0, 1, 2, and the same on the other side, but we won't worry about that. Our nodal lines are going to be in between like this. Terrible drawing, but bear with me. Where this is 0.5, 1.5, and 2.5. Our 2.25 is going to be between 2 and 2.5, so somewhere there. Now to view that in another way, say we had a screen set up and we were to plot the amplitude of the light hitting the screen, for a double slit pattern it would look something like this. Where our 2.25, if it was say halfway in between 2 antinodal line and 2.5 nodal, so halfway between these two, it would be about here, and we'd be seeing a point that would have something like half brightness. The important distinction here is that this is not a double slit pattern. This is a diffraction grating. And because it is a diffraction grating, the antinodal areas are extremely sharp and defined, and the dark nodal areas are wide and very distinct. So it looks something like this, where our 2.25 would be something like here. And if I'm just going to draw the fourth one out so you can really see what I mean, the point I'm making is that this area, this 2.25, will be completely dark. Once again, that's because it's a diffraction grating and the lines are very defined. They're not smooth like you might see with two source interference. They are sharp and defined. So let's put that into words. This region will be dark as it is between antinodes. This is different to a double slit where the antinodes are more spread out and the point would not be completely dark. And we're done.